For the final leg of this section, I want to focus on functions whose domains are subsets of R. Because so far we've seen general constructions of limits which work for subsets of C, and in the real case there are some limits which are just simply don't make sense in the complex case, but which occur if you just restrict to functions on subsets of R, so on functions with real domains. In this rest of the section I will be a little bit sloppy because I will mostly give definitions and examples, but a few theorems, but I will mostly skip the proofs because it's actually everything would be very similar to what I've done before. And so in some parts I've included the proofs in the lecture notes, in some parts I didn't because it would be just an easy generalization of this. So just keep in mind everything that I will skip is kind of works similar to these limit constructions I did before. So there won't be that many theorems in this section, so mostly I will just present you some constructions that we will see later on, probably in some examples or something, but just mostly introducing terminology and introducing some additional notions. Okay, I will start with a construction with a kind of motivating example for this construction. Namely, we consider a function from R to R, and a very simple one. F of x is given by x if x is negative, and by x plus 1 if x is non-negative. So the graph of this function would be very simple. So left of the y-axis we would just have this. This is just the function x. And here we've simply got shifted, this one shifted by 1. So if 1 is, for example, here, then it goes on like this. And this point here is included, and here, so this saying that for x value of 0, we are here, and we take this value here. So here's x, here's f of x, always label your x's. Here we've got a different situation, because here, of course, if we kind of would restrict to r without 0 and would just consider the function without this point here, this, of course, when the limit in 0 wouldn't exist. Because this function is obviously non-continuous because it has a jump in here. So this function is not continuous, but you can see some things because here if you, so first of all, yeah, f is not continuous, so not continuous in 0. But first of all, the restriction to r without 0 is continuous. Whoops, here goes the layout, but the restriction to r without 0 is continuous. And if we restrict to everything which is on this axis and on the right-hand side, if we just forget about this left branch here, then it's continuous too. So if we restrict f to this closed interval from 0 to plus infinity, this is also continuous. So here we've got continuity. So in general, we don't have a continuous extension of this function here, of the here's the restriction bar missing, like this. So this restriction does not have a continuous extension in 0, so there's no limit in 0. But if we just would consider points from the right-hand side, then we have a limit indeed. And also from the left-hand side, we have a limit, which is just not the value of the function here. So if we approach this from the different sides, this would have limits. So in general, approaching 0 and just very sloppy from one side, and I will make this precise in a bit, from one side is fine. So this would work. So this motivates the following definition, because we make a definition by saying we just take limits that we get by coming from the one side or the other side. This goes as follows. So let me give this formal definition here, and just this notion of coming from the right or coming from the left needs to be formalized here. So the general construction, we have a subset of R, which is the domain of our function D. F goes from D to C, so its values may be complex. This doesn't change anything. And we have a certain point in R at which we want to consider these limits coming from one side. So to come from one side, we just, here the idea was to restrict to kind of everything right of the axis and left of the axis, and the same we need to formalize here. So on the one side, we take a set which I call D minus, and this is simply D intersected with the open interval from minus infinity to a. So this is everything what's on the left side of a. And similar, I take D plus. There I take everything which is to the right of a. which means I take D intersected with the open interval from A to plus infinity. Okay, so I've got these two, and so the idea is now to take the limits of the restriction to one of these two sides and to consider this as this left-hand limit and right-hand limit, as we shall call it. So this is the main idea. So first of all, from the left-hand side, we say that f has a left-hand limit in A if, first of all, A is an adherent point of D minus. Otherwise, it's doesn't make much sense because we're kind of too far away. And the restriction from F to D minus, if this has a limit in A. And this left-hand limit gets some special notation, namely we then put limit and now x, and now we take an arrow which goes down and now diagonally to the top here, to the right. This means we're below A, so we're coming from below and we're tending towards A, but we're coming from below. So that's notation. Some also make just a vertical arrow which just points to the top, but I prefer this notation here. So this would be the left-hand limit, and this would then be the limit of x to A of the restriction of f to D minus of x. Okay, so this is the idea of just coming from the left formalized. Okay, now you can guess how the situation from the right works. So f has a right-hand limit in A. First of all, if A is now an adherent point of D plus, and the restriction of f to D plus has a limit in A. And then, of course, we also introduce some notation, and this time this means we come from below, and now this would mean we come from above and go towards A. So we do just the different arrow, namely we go this diagonal arrow. So we're going down and we're going towards A. This is the notation for this right-hand limit. And this is then by definition, so the limit of the restriction to D plus, limit of x to A of the restriction of f to D plus of x. Okay. This is the right-hand limit. Of course, here I said that this function is obviously non-continuous, because here, in this situation, we would have the left-hand limit and the right-hand limit would both exist in 0. So here, the left-hand limit would be 0, the right-hand would be 1, but obviously they do not coincide, and that's the problem. And we also want to introduce some formalism for the situation where just one of the two exists. So where there's just the right-hand limit and the here we would have the situation that the right-hand limit exists, and that it coincides basically with this limit of the restriction here. So if this was really, here the function was already given, and we've seen the right-hand limit coincides with the value of f at the point that it holds by definition, but the left-hand limit exists but doesn't coincide with the value of f at 0. This is the correct notion of saying it. To formalize this and to get some generalization of continuity in this case, we first need to assume that A is in the domain of D, otherwise in the domain of F, so otherwise this doesn't make sense to formulate what's coming now. And now I say that F is left continuous. So note that F is just a map, right? So there's no requirement of continuity or something. Keep this in mind. So it's left continuous in A if it has a left-hand limit. If f has a left-hand limit in A, left-hand limit in A, and I want that this left-hand limit coincides with the value of f at this point, which makes sense because A is in D. So x going up to A, limit of this is f of x is f of A. Okay, now you can guess what's coming next. So now this is left continuous, and of course from the other side we get the notion of right continuity. So again, assume A in D, F is right continuous. right continuous in A if f has a right-hand limit in A, and this right-hand limit coincides with the value of the function. So x is going down to A, so the limit of this is f of A. Okay, this is right continuity. And just as a very simple example, something we've seen, so this would be an example. So here this function would be right continuous because the right-hand limit coincides with the value of the function, but this is not left continuous. And another example that we've already seen, let me just write this down once again. That's example 354, the Heaviside function. This was the map which takes x to 1 or to 0, where we go to 1 if it's x is bigger than 0, or 0 if x is smaller than 0. And in the same way as this, we've got the same phenomenon. If we come from the right-hand side, so if we come from values bigger than 0, we get as the limit 1, which coincides with the value, opposite to the, not the case of the left-hand side, because there the value would always be 0, so the limit would be 0. And so, so this is, let me just write this here, this is right continuous, but not left continuous. Oh, sorry for squeezing here, just want to save some space. So that's the idea here. And now you might ask, so how is this left continuity and right continuity connected to continuity itself? So when does the limit exist? And now if you see these two definitions, there's a statement that holds that's kind of quite what you would expect, although the proof is not entirely trivial, but I will not discuss it here. So let's say we have a subset of R, we have an element A of this subset D, and we have a function with domain D and complex values. Then f is continuous in A. If and only if it's left continuous and right continuous. So these two together imply continuity. The proof is a bit technical, but the idea is kind of, I mean, if you see how this left-hand limits and right-hand limits are defined, it's kind of intuitively clear, though the details need to be checked here. So it's a bit tedious to write things down, but it's not very hard. So it's left continuous in A and right continuous in A. Sometimes if you have, this is especially useful if you have some case-wise defined functions or functions that on some interval are defined by one thing. So if we have something case-wise like this, and we have like totally different things, we just need to check what happens at the ends of the intervals where we have defined these things and to see if the limits coincide, and then can conclude that the function itself is continuous. So this is the way this is mostly used, this theorem. Okay, so remember, so we will see probably some functions later on which are kind of defined on certain intervals, in different ways on different intervals, and kind of we need to see the connecting points if it kind of glues together continuously. So the proof of this I've included in the lecture notes, but I will not discuss this here. Okay, but yeah, so far, yeah, this is not that complicated actually. I think I might erase now anyway because I'm now starting a new concept, and so let me just erase. The next thing I want to discuss is what happens if functions over the real numbers have some approximate behavior if the input of the function becomes close to plus infinity or minus infinity. So what happens, how does this approximate a certain value for increasing values or falling values of x? For example, the hyperbola 1 over x, the very simple thing we know, you know from high school, or basically we've basically already seen this, but that this goes to 0 if x becomes bigger and bigger and bigger. So we kind of approximate a certain value, and we want to see this value as the limit of the function in infinity. So in plus infinity or in minus infinity. So this, that's the main idea here. And this also I want to formalize, and by giving the just the explicit definition once. So we see it. So how can we express this if we want to formalize what a function does for very big or very small values? So let's see. We again take D a subset of R and f a function from D to C. So, in the first case, we want to see what happens if we go to plus infinity. This, of course, requires just to make sense that d is not bounded from above, because otherwise nothing could go. I mean, we don't have big values, so we simply cannot ask these questions. So, assume d is not bounded from above. So then we say that f has a limit in plus infinity if there exists a number, which will then be the limit, some number L in C, such that the following holds, and again we need epsilons, for all epsilon bigger than 0, there is some real number R, such that if we have kind of passed this number R, everything will stay epsilon close to L, which means f of x minus L is smaller than epsilon for all L, sorry, I need a bit more space, for all L which are in, sorry, not L, for all x in the interval from a to plus infinity, and of course intersected with our domain, otherwise it doesn't make sense. So if once we've crossed R, we never, we always stay epsilon close to L. And if this goes for every epsilon, then we have this limit of L. We can, maybe let me draw a picture just to illustrate this. Assume we have some function, let's say we have a limit L, which is somewhere here. So assume the case of a function from R to R, not context, although it's the same thing. So let me just draw this horizontal line here. And so we now want to see check a function which kind of approximates this value. So kind of we're coming closer and closer and closer and closer. Assume it's defined everywhere, and then, so this means approximating the value. So this definition now says, so for each epsilon, we want to stay epsilon close to this L. And so this means we kind of, first of all, we draw all values which are epsilon close to L. So assume we have here some number, the number L plus epsilon. Here we would have L minus epsilon. So we need to stay within this neighborhood, within this range here. So if I draw these horizontal lines, this means that the points of the graph need to stay in this strip, so in the strip bounded by these pink horizontal lines, from a certain point on. And as I've drawn it, so if you now assume that this behaves as I want it to behave, this means that we have found some number, for example, anything which is beyond here would be fine. So of course, the function could do funny things in between. This is now of course a very nice function, but from some point on, it's kind of behaving nicely and not leaving the strip anymore. So we can take any value here. Let's say this is R. Then, if we now draw this vertical line here, we see that if we write off this vertical line R, everything is in this pink strip, and so we're happy, right? So this is what this definition says. Okay, so this is the formalization of something going to infinity, and in this case, of course, we introduce notation. Namely, we just write it as you might expect. Namely, we say as x goes to plus infinity of f of x, this is then simply this limit L. Okay, this number L. Okay, the same thing, of course, applies if we go to minus infinity for these functions. And there we have a similar situation. First of all, let me just copy this. So assume d is not bounded from below. That's the analogous situation. Then, now I cannot just copy the layout since I messed it up anyway. Now we say that f has a limit in minus infinity if there exists an L in C such that, now a similar thing. For all epsilon bigger than 0, there is some number, some real number R in R, but now we want that everything to the left of this number stays within this epsilon range, which means just taking this, taking just the analog definition of this, we take f of x minus L should be smaller than epsilon for all x left of this R, which means for all x in minus infinity to R, and of course intersect with our domain. So this says the same just from the other direction. So I could just mirror this image to this side, and then I would get the same notion here. And of course, in this case, we write the limit of x going to minus infinity f of x is L. Okay, so these are very straightforward definitions. And let us check some example, because I've already mentioned this hyperbola 1 over x, and you can generalize this, and this is now kind of a very important example, because this is something you really need in practice. This kind of that occurs very often in your computations. First of all, we take some rational number, q, with q bigger than 0. And we consider the function f from 0 to plus infinity to r, f of x is 1 over x to the power of q. So this generalizes this hyperbola 1 over x that I briefly mentioned. This will be the case q equal to 1. Of course, here we need a rational number because we haven't yet defined powers with real exponents. This is what we do in the next section, so it's a little preview to this. But this kind of is the general thing, so this generally behaves like a hyperbola would be the idea, and we really want to show that it has the same approximate behavior. So, for this function, we want to, of course, study what happens if we go to plus infinity. What does this function do? And we know that for q equal to 1, it goes to 0, and I want to show that this really holds in general in this situation. Okay, so we do this really by definition of this limit. So for each epsilon, we need to find some real number such that this holds, and this is something you can really explicitly compute at this point. Namely, that epsilon bigger than 0 by a statement from quite a while ago, by corollary 153. I'm just mentioning this for completeness, so you don't, so for completeness of the argument, so this is not really, you don't need to know all these numbers. There exists a natural number n in n, such that 1 over n is very small, namely smaller than some positive number, and I don't want epsilon itself, but epsilon to the power of 1 over q. This is some positive number, and we've seen that we've always confined such a number n such that this holds. Okay, this is what we know by this corollary. But then we get a nice consequence, namely then it follows that 1 over x is, so if we take x to be bigger than n, then 1 over x is smaller than or equal to 1 over n, which is smaller than epsilon to the power of 1 over q. So this holds for all x in n to plus infinity. So we already have found a value such that this becomes quite small. And now if we want to go to a function, we just need to take the power of q. Namely, this shows that the absolute value of f of x, and we should read this as f of x minus 0, because I want to show that this condition here is satisfied with L equal to 0. This is, of course, the absolute value is unnecessary because these are positive numbers. This would be 1 over x to the power of q. And we know, we have seen about powers that they have these monodicity properties. So if this is smaller than this, then this is smaller than or equal to 1 to n to the power of q, and this is smaller than by taking this to the power of q, so this is epsilon for all x in n to plus infinity. So given some epsilon, we have found some real number, just coincidentally it's a natural number, which doesn't matter, but we have found some number that from this number on we stay within this epsilon range of 0, and this means that the limit from x going to plus infinity 1 over x to the power of q is 0. Okay, now we've seen that this has this hyperbola behavior in some sense. We cannot just formulate this here for negative arguments. So x is really just a positive number, and we could not just replace it by a negative number. If I would have an audience in here, I would ask why. The problem is that this is some rational number, so this might involve taking roots. Right? So x to the cube might be a power of some root, and roots only exist for non-negative numbers, and for 0 this is not well defined, but we cannot just insert negative numbers in here. But there is an example where we can, namely if we don't have the roots, namely if q is not it's not some arbitrary rational number, but a natural number. So in this case we can also consider minus infinity, and this is what I will do next. So we take n and n, and take f now defined on r without 0 to r. F of x is 1 over x to the power of n. So this time we can insert negative numbers, that's no problem, there are no roots, everything's fine. Okay, so now we know from this that for going to plus infinity we get this limit 0, And we have seen, I mean, you know that how these hyperbolas behave, probably from high school. But now we want to check that if we go to minus infinity, it also goes to 0. And this is, yeah, basically shown in a very similar way. So, namely, given some epsilon bigger than 0, we again take an n in n with 1 over n smaller than epsilon to the power of 1 over n. This is so similar as before. Sorry, wrong n. Small n, of course, here at this point. And now, if we are, so we need to show that now for very negative numbers, so to say, so that's not a very mathematical statement, but for very negative numbers, in terms of this n, we have that this expression stays smaller than epsilon. And this is what we will do now, namely, so for all x smaller than or equal to minus n, so we just put a minus in front of here. What will we get here? Then we get that minus 1 over x is smaller than 1 over n. Simply by just yeah, multiplying with a minus and so first of all we have to invert, which kind of flips the direction of the equation once. Sorry, this. So inverting flips it once, and then multiplying with a minus 1 flips it twice. So we get again an equality in this direction. So now what does this mean? Now it depends, so if we take the powers of n, now it depends if we take odd powers or even powers, because then this is either positive or negative, so we have to be a bit careful. So this means basically, yeah, we have to separate the two cases, namely for n odd, this implies that minus, and sorry, I again said something wrong, so I just needed to edit this at this point. From this inequality we can derive something nice, because x is supposed to be a negative number. This is negative, so this is negative, which means that this expression is positive. So we have a comparison of two positive numbers here, and we've seen that if we kind of take powers of this expression, this inequality stays as well. So if we take this to the power of n and this to the power of n, we get the same expression. So if n is odd, of course this power would be minus 1 to the power of n, 1 over x to the power of n. So minus 1 to the power of n, if n is odd, we get a minus. So this means we get this expression is smaller than or equal to 1 over n to the power of n, which is by assumption, or just by construction of n of the large n smaller than epsilon. So for, not an implication, sorry. For n even, so now we have minus 1 to an even power, so this vanishes, so we get 1 over x to the power of n smaller than 1 over n to the power of n, again smaller than epsilon. But now we see, if we take, yeah, so if we combine these two statements, we see that this number here, if n is an even number and x is negative, this is something positive, so this would be the absolute value of this expression. This will coincide with its absolute value. If we take a look at this, if n is odd, this expression here is negative without the minus, so this fraction here would be a negative number. So we put a minus in front, which makes it again positive, which again would be the absolute value in this case. So these two combined show that the absolute value of 1 over x to the power of n is smaller than epsilon for all x in minus infinity to minus n. So this really shows, again, the same argument as before, that this has kind of limit 0, because this you can read as 1 over x to the n minus 0. So this shows, since epsilon was arbitrary, this again implies that if we go to minus infinity and take the limit here of f of x, we get 0. Okay, so this completes the example. Yeah, a few remarks and results after erasing. Some remarks on limits in plus and minus infinity. So this is remark 358. First of all, there's something I don't want to prove, but which you may just use because kind of the proof would be revisiting old arguments again. Namely the roots from theorem 350. This means limits of sums of function, of products of functions, of quotients, and so on. This also holds if we go to plus or minus infinity. So if we have these divergence, these conversions in infinity, we get again that the limit of a sum in infinity, if both exist, it's the sum of the two limits, and so on and so on. And since this is really not very exciting to prove, and this is not very hard, I will just not prove them and just allow you to use these rules. So the rules from theorem 350 hold for limits, hold for limits in plus or minus infinity as well. So this, I will not formulate this as a, without proof. I will not formulate this as an individual theorem because it's just a bit too much effort. It's just the direct translation of these results. And something that's maybe not obvious, that's basically now for the connoisseurs who want to know, who are really interested in the details here, namely the definition of limits in infinity. They actually generalize the definition of the limit of a sequence. So they generalizes limit of a sequence. Namely, what's a sequence? A sequence is actually a special case of a function if we take complex numbers. Namely, if we take the domain to be n, a sequence is by definition nothing more than a map from n to the complex numbers or real numbers or whatever. But this is the definition of a sequence. So if we have some a from d going to c, which is then a sequence, then you can really check that the two notions of limits coincide. I will not prove this, but this is basically, they really, you just need to write down both definitions and then you almost immediately see that they are just the same definition. So one checks that, yeah, the limit, now I write this really technical here, of x going to plus infinity a of x, which would be the limit of the, yeah, of this as seen as a function. This is actually the limit of the sequence an, where an is defined as a of n for all n in n, as we usually do it. So we really have generalization of this definition here at this point. Okay, this is just for kind of people who are interested in this. Okay, so much for that. We've seen for limits in a particular point in C that we can characterize this by limits of sequences. So we had this sequence, this theorem which says that something has a limit if kind of all sequences, if f of the sequence converges to some value. And there's a similar statement for limits in plus or minus infinity, which again I will not prove in here. So if we have D subset of R and F a function from D to C, so part A, the first part we again need to assume D is not bounded from above. Then the limit from x going to plus infinity f of x is equal to L. This is the case if and only if for each sequence, and now we can of course have convergence, but we now need kind of convergence to infinity, which we didn't explain, we called it divergence to infinity. So a divergent sequence which becomes infinitely big. So for each sequence in D, which diverges to infinity, so with, as we've noted this, sequence xn, I have to give it a name, in D, with limit plus infinity, so which diverges plus infinity. For each of these sequences, it holds that limit n going to infinity of f of xn is L. Okay, and the same for the other direction, which is now a bit tedious. So I will just copy what's written here. Assume now this time this is not bounded from below. Then the limit for x going to minus infinity, f of x is equal to L if and only if for each sequence xn in D with which diverges to minus infinity. So here's the difference. Here's a minus. It holds that, yeah, this converges to L. So only difference is there, the minus here. Okay, so this, yeah, as I said, the proof is in the lecture notes. I will not give it here. It's actually a bit tricky, but So this is proof in the lecture notes. You can read it up there. Yeah, but this is kind of everything I want to do for now about these things. We will see quite some examples, and you will also have to compute some examples in the exercises. So this is basically just the construction, and I don't want to do much theory about them because these are kind of limits or notions that you actually need in practice. So you should really practice this by doing the exercises. Okay, now as the next thing, I want to give a theorem which kind of is a straightforward analog of the analogous result for sequences, namely what happens if we kind of compare functions if we have some inequality between two functions, the same as we had of inequalities between sequences. Then we have seen that an inequality between two sequences leads to an inequality of the limits. And this is the same in the case of functions, and again, probably most of you or many of you already have a notion of what I mean, but of course I need to write this down. Okay, namely, this time, of course, we can only talk about real functions because otherwise inequalities don't make sense in C. So we have two real functions. And first case, we take an adherent point. So we take a limit in some particular adherent point of D. And we assume F and G have both limits in A. Both have limits in A. And now in the case of sequences, we've seen that if we have an inequality that holds for almost every n, so only for large values of n, we need that that there's an inequality between two sequences. Here we have a similar thing, so we need to generalize this notion of something of this almost every n. And if you think about what this almost every n says, kind of if we're sufficiently close to this limit, then it behaves nicely. And sufficiently close to this limit is something that we have formalized in the beginning of this section. Namely, if there exists a D neighborhood, which I call A of small a, with f of x smaller than or equal to g of x for each x in this neighborhood. Right, so, for all, not in this neighborhood, but for all in this neighborhood intersected with a domain, because A is of course not necessarily contained in there, so everything close to A where we are inside the domain of our functions. So if this holds, so close to the point where we consider the limit, then if this holds, then we get that the limit of x going to A f of x is smaller than or equal to the limit of x going to A of g of x. Okay, so there we get this inequality. And the same is now true for the limits in plus and minus infinity. And this is also now a bit tedious. I will try to keep it short. B, again, assume D not bounded from above. And that both f and g have limits in plus infinity. And now we can formalize this kind of for almost every n a little bit simpler. If there exists some value r in R with f of x smaller than or equal to g of x for all x in R to infinity intersected with D, then let me save some space here because I don't want to start a new blackboard with this. So then the limit of x going to plus infinity of f of x is smaller than the one of g of x as x goes to plus infinity. Sorry, I hope it's still readable. And of course the same thing for minus infinity. So you see it's a bit tedious, this part. So C, I can now copy basically from this blackboard. That's a bit, I'm cheating a bit, but you know what I mean. So assume the domain is not bounded from below and that both f and g have limits in minus infinity. And if there exists some R in R with f of x smaller than or equal to g of x for all x in minus infinity to R intersected with the domain D, then it follows that here the limit of x to minus infinity f of x is smaller than or equal to the limit of x to plus minus infinity g of x. Okay, so we have this inequality here as well. And also here I want to be sloppy with the proof because this is now really tedious. You basically can kind of use the sequence criterion, so this theorem that I just sketched here, and then the same property of sequences. So yeah, basically this is only what you need to combine in this point. And so the theorems you need for this, so the proof would be just combine the corresponding result for sequences, which is theorem 226. Then we need theorem 349. This was this sequence criterion for limits in the point. So this was for limits to plus infinity, and this here was for the limits in some adherent point A. And of course this theorem here, so 359. And I will omit the details here because it's just taking too much time to do all this. Right, so this is something you can really use to do computations. And I want to leave kind of the examples basically to you because you will kind of, yeah, can be able to use this in the exercises at some point. Okay, and of course, this is something I don't want to write down in detail. Similar to this, once we have these inequalities, we can also define something which resembles the squeeze theorem. So remark 361. We can derive a squeeze theorem for functions. From theorem 360. Meaning if I have three different functions and they satisfy like f of x smaller than or equal to g of x smaller than or equal to h of x, and the outer two functions f and h have the same limit in the point, then the one in between has no choice and has the same limit in this point as well. So this is basically by combining this inequality twice and yeah, going along. So this is just a direct consequence from, yeah, or directly shown as a squeeze theorem for sequences, and you can use this as well. Okay, there's one more construction in this section, and I need to erase first. The final notion I want to introduce in this section is the notion of so-called improper limits. This is basically formalizing the notion that if we kind of approximate a point, the function goes to infinity. So it becomes infinitely big or infinitely small, going to plus or minus infinity. This is something that we haven't formalized yet, but this is defined in a similar way. And I just want to give you the definition and an example, but not doing further theory with it. This is just something you might need on your way when practically discussing functions. So, I'm only doing this for functions, again, defined on the subsets of R and going to the real numbers. There are kind of versions for this for complex numbers, but these are not too important for now, so let me just skip them. Okay. A. Let A be an adherent point of the domain, which does not lie in the domain itself. So really some adherent, a true adherent point, which is not part of D. We say that F has the improper limit plus infinity in A if kind of for each value in R, so for all R in R, we find a neighborhood of this point A. So when we're close to point A, we have only values which are bigger than this R. So it's really exploding beyond R. This means, so for all R in R, there exists some delta bigger than 0, such that f of x is bigger than R for all x in the interval a minus epsilon, a minus delta, a plus delta intersected with the domain. Okay, so let me also draw a picture of this. Assume we have some function here, x, f of x, and we have some point A. So where the function is not defined. And assume it's kind of defined everywhere else. And we have this notion that the function goes to infinity. So let me just draw a vertical line here to help me draw. So a function which would be looking like this, might do funny things here, but it doesn't matter. Okay, something like this. So this goes to infinity in this notation. And the idea is now, if I take some real number r, I want that for some neighborhood of A, where kind of very close, so very close to A, the values only become bigger. And this is the case here. Let me just draw this horizontal line. So I need to know that the part of the graph over this set needs to be above this horizontal line. So it means we need to find some delta. And kind of if we now take, so from here on and from here on, we are just above that. So we can just take some delta which is at most as big as this. So let's say we have it like this. These values, oh, sorry. This is a terrible drawing. Oh, no, this. Anyway, you see what I mean? So if we're within these two, should be vertical lines, but we stay within these vertical lines, so we go here up to infinity, but we do not ever cross this horizontal line again. This is the important thing here. So whenever we are in this vertical strip, we do not cross this line again. Okay, this is what this definition says. And in this case, of course, we write the limit of x going to a, f of x is plus infinity. So just as for divergent sequences, we just use this limit notation here. Okay, the same, of course, we have for negative, for functions going to minus infinity. So if we just would mirror this image upside down, we would have something going to minus infinity. And there I just want to be brief. So again, we take an interior point, and we say f has the improper limit minus infinity in A. So the same minus infinity in A. And now almost the same definition for all r in R, there exists some delta bigger than 0 such that f of x is smaller than r for all x in a minus delta, a plus delta intersected with d. Okay, and now the final thing I want to introduce, and this is now then this tedious part is over, is if a function has the improper limit infinity or minus infinity if we go with x to plus or minus infinity. So what's happened for infinite values? There we get, just have to basically write down everything again. So assume d is not bounded from above. There we say that f has the improper limit plus infinity in plus infinity if, and now, similar definition, but we just need to be a bit careful now because we do not need to work with delta neighborhoods of a point. Namely the following way, for all r in R, there exists a real value c in R, such that f of x is r whenever x is bigger than c. So this is bigger than r for all x in c to plus infinity intersected with d. And in this case, so we write, let me just squeeze this here in between, limit of x going to plus infinity is, of f of x is plus infinity. Okay, now the same thing for going to minus infinity. So again, assume d is not bounded from above. F has the improper limit minus infinity in plus infinity if, and again, we write limit of x going to plus infinity, f of x is minus infinity. If for all r in R, there is some c in R, such that the opposite inequality holds, f of x is smaller than r, for all x in minus infinity in plus, c plus infinity, intersected with d. Okay, now, in the same way, we can define improper limits as x goes to minus infinity. And since I don't want to write down everything again, and this is quite easy for you, I mean, the only thing that would differ here is that this interval will become minus infinity to c instead, and then the same construction would go down as well. So I just write analogously, and we'll just use them in what's coming, improper limits as x is going to minus infinity. So we call this improper limits in minus infinity, and so on. Okay, not very exciting, but let me give you a nice example. Namely, let us revisit the function we already visited before when we went to see what it was doing if we go to infinity. Example 363. We again take a rational function q, which is positive. And we consider again the function from 0 to infinity to r. F of x is 1 over x to the power of q. Okay, so what we want to show now is what happens if we go to 0. And we know from the hyperbola that values go to plus infinity there. So if we take 1 over x, and we will see that this indeed holds true in general. Namely, let c be some real number, then there exists some number n in n. Again, we can choose an n such that 1 over n becomes very small, and by very small I want that this is smaller than 1 over c to the power of 1 over q. Okay, now we can always find such an n as discussed before, and now to find our delta. So the delta neighborhood of 0 such that inside the interval, which would here be just 0 to delta, so such that there the functions, the values of the function become bigger than c. So for this purpose we just put delta to be 1 over n. So this is indeed working in here, because we know that if x is in this interval, then we know by this inequality that x is smaller than 1 over c to the power of 1 over q, which is equivalent to saying that x to the q is smaller than 1 over c for all x in 0 delta. And just if we take inverses in this inequality, it flips. Namely, this implies that 1 over x to the power of q is bigger than c for all x in 0 delta. And yeah, this would be just kind of minus delta. Delta intersected with the domain, so with 0 to plus infinity to go really line by the definition. And yeah, so since c was arbitrary, this shows that the limit of x going to 0, f of x, is plus infinity indeed. So the graph of f is something like this. So just I already mentioned the hyperbola that we draw this once. So if we're going to 0, we go to infinity, and we go to 0 here. In fact, we could see that it's strictly monotonically decreasing. So here we go to infinity, here we go to 0. Right, so this is how these hyperbolas behave. Okay, then as the final example, I just want to mention something, and I will not prove this because this easily follows from the rules for inequalities and powers. Namely, for each k in n, you can see that limit x to plus infinity of x to the power of 2k, so with an even exponent, that this is the same as the limit of x going to minus infinity. This is something that's very easy to see because the sign doesn't matter here, it's even. And in both cases, it's plus infinity. So here we've got this notion that this improper limit of plus infinity as we tend to both directions of the real line. And also for the odd case, you can see that the limit of x going to minus infinity, x to the power of 2k plus 1 is minus infinity. Like, if you remember x squared, that's the standard parabola. If you take a look at x3, this is kind of this thing which kind of is bending down again, and no, it's the mirror. So yeah, from your perspective, it's up. Yeah, okay, something like this. So in the odd case, so for odd exponent here, we get that this goes to minus infinity, and if x goes to plus infinity, x to the 2k plus 1 we get plus infinity as well. Okay, this is something that's easy to see, so I will not prove this, but this is some kind of the most basic improper limit, I think. Okay, and as I said, you will see a lot of computations with limits in the exercises, and yeah, you really need some practice. So we won't go too much into theory about these, but we will definitely need them in the following chapters in the construction, for example, of derivatives. Okay, so much for that. See you in the next section.